Thanks very much, Edward, and thanks for inviting me to talk online. It's great to be able to reach a wide audience this way. As Edward said, I'm going to talk, before I talk about my research, talk a little bit about the Marie Curie and Enterprise Ireland CoFund Fellowship that I am funded by. Okay, yeah, so I'll talk a little bit about the fellowship itself and then give an overview of natural language processing in general before I talk about how it's applied in the business context that I work on for Corlytics. And then I'll show some results from the project so far, results in progress, and then take questions at the end. Corlytics are an Irish RegTech company based in Nexus UCD, a spin-out from Nova UCD. And they provide regulatory risk intelligence and analysis to global financial companies. So they have a focus on multinationals globally, large banks and financial organizations, and they collect documents online, such as regulatory enforcements and news about regulation, and provide analysis and synthesis of them and intelligence from them to companies. They have an expert legal team that annotate regulations and enforcements by different categories, and part of the project I'm working on is to automate some of that to some extent, or to supplement their work with automation. And I have a background in computer science and linguistics, and I did postdocs in the UK working on applying NLP methods to research in social science and humanities. And the advantage of you might know about the Marie Curie individual fellowships, which are EU postdoc fellowships. This is a co-funded version of that, which is partly administrated and funded through Enterprise Ireland. And the idea is that you are paired with the Irish business, and that you work on a project where the research aspect ties in with the business goals of the company. And it's a great deal for both parties because it's free for the company. The researcher, you get a lot of, it is a research project. You have your own time to do the research, as long as it ties in with the aims of the company. You're not treated as an employee of the company. Those fellowships are well thought of, and because they come through this co-fund route, they're maybe a little bit less competitive than the traditional ones. So it's really a good deal for everyone involved. The one condition attached to it is that you have to be the researcher has to be coming into Ireland from abroad. So in my case, because I had worked in the UK for a while, there's a certain amount of time, I think it's 4 years, that you have to be outside of Ireland before you come back in. But contact Edward if you're interested in the next round of this, either as a researcher or as a company, and CeADAR can give you the full details. Okay, so brief overview of natural language processing. Sometimes the acronym NLP, if you type it into Google, the first thing that comes back is articles about neurolinguistic programming, which is a different thing altogether, a type of hypnosis. So that's not what we're talking about. We're talking about automated or computational processing of natural language. So the slight difference between this and text analysis is that text analysis could be any kind of text document, whether it contained programming language or genetic code or something. And natural language processing specifically deals with human language, natural language. It's also sometimes referred to as computational linguistics or corpus linguistics. There's slight differences in these meanings. Computational linguistics tend to focus on the applied side, using computational methods to work with language for purposes like translation and things like that. Whereas corpus linguistics focuses on answering questions in linguistics, questions about language, specifically focused on the nature of language using corpus methods. And these are some of the applications. This is, I suppose, quite widely known at this stage. NLP is used for speech recognition, translation, dialogue agents and bots, document classification, topic modeling, knowledge extraction, summarization, and information retrieval. So lots of different ways of getting information from documents, classifying language, and analyzing language. And there's a kind of historical tension in the way that computer methods are applied to linguistic questions in general. So Noam Chomsky, who was one of the kind of transformed theoretical linguistics in the 20th century with theories of syntactic structures and transformational grammar. Chomsky was very against the idea of using any kind of probabilistic or a statistical analysis of language. That, you know, he thought you couldn't learn much about human language by counting how words co-occurred with each other. And then in engineering applications, there's a well-known quote, or supposed quote at least, from IBM saying, every time I fire a linguist, the performer of the speech recognizer goes up. So this just, you know, this kind of trade-off is very familiar in lots of domains today, that you would like to add more theory into the models, but in practice, theory light and data heavy models tend to outperform, at least in traditional benchmark situations with you know, kind of ideal conditions for validation. And this continues in NLP today. The methods that achieve state-of-the-art performance on benchmarks are deep neural network models. So you've probably heard of BERT or GPT-2. They've just released GPT-3, or at least they've released a paper about it. Something like 175 billion parameters, and the parameters in RAM are 700 gigabytes. So I'm not quite there yet, but these models have the best performance on these kind of data sets. And for the ones that are old, and by old here we mean like, you know, 12 or 18 months, there are you know, very good Python libraries. There's a package called Hugging Face, which kind of wraps all of these neural network models, and is quite easy to use. And then there's kind of a more traditional method, which involves extracting features from documents using natural language processing library, and then doing a kind of traditional classification or regression with regularized regression or support vector machines. And from the NLP point of view, these packages, Spacy and GenSim in particular, are what I would recommend for doing NLP work in now. So there's an older package called NLTK that a lot of people use, and it's still very useful for simpler tasks, but Spacy and GenSim have really great documentation and full features with all of the latest methods. Yeah, and then the trade-off between these two methods is that, especially for something like classification, it's nice to be able to tell which linguistic features cause the outcome of the classification, which features are associated, which phrases or entities or words are associated with a given document classification. And with something like a ridge regression or an elastic regression, you can get coefficients back, you know, that show each phrase and how much it's associated with a given outcome, whereas that's more difficult to do with neural network methods. And CeADAR has another project going on at the moment led by Luis. It's on interpretable text classification. So they'll be releasing something that looks into the interpretable stuff in more detail at some point. Okay, and you might also have heard of word vectors or word embeddings. So these are ways of making representations of words or phrases so that you can measure distances between words or find analogies between words. And there are two popular libraries there, Word2Vec and Glove. These word vectors kind of were you know, briefly used as input to things like classification models, but now the latest these BERT and GPT-2 transformer systems are kind of, it's not as simple as putting word embeddings in at the top. It's a full end-to-end model with more than one word embedding layer. This is what the output from a syntactic parser looks like. So this is an example output from Spacy. This shows you that packages like Spacy can take a document for a given sentence and find for each word the root of the word. So go from the plural to the root and kind of normalize things like pronouns. so tag it with its part of speech. And then there's also, this encodes a tree. So for each noun, you can tell what its object and subject are, which is useful for designing kind of custom features for things that you might not have enough training data for, or that end-to-end model won't pick up. They also give you outputs like this, which can tag entities in the text. And there's a much longer list of entities than this. This is just 3 of them: organization, geopolitical entity, and monetary value. So this is useful. Obviously, it doesn't solve any problem. There's a good example in the work I do with Corlytics, where we would like to, for a regulatory enforcement, we would like to know what the fine was. So if a company breached regulations, how much were they fined? And you think this looks great because the package can extract amounts of money. But of course, an enforcement document talking about a fine because of breach regulation will contain lots and lots and lots of amounts of money relating to different things. So it's finding which one relates to the fine or which one relates to the particular variable you're interested in. That's important. Okay, so for the rest of the talk, I'm going to mostly talk about a classification problem. So that's one of the most common applications for NLP, document classification. So we want to take a document and give it a label or a place in a particular taxonomy. Related to this would be the problem of estimating a continuous property. So this is often, the example usually referred to here is sentiment analysis or toxicity in text, for example, in a tweet or in a review on Amazon. And that's, on a continuous scale between, a very bad review or a very good review. But that's, the classification problem is just an extension of that, where for a continuous problem, you want to apply a threshold, and above that threshold, we will give the document a label, and below the threshold, we won't give it the label or give it a different label. One way of approaching this is to define a dictionary of relevant terms for classification, so to restrict basically the feature set extracted from each document to a dictionary that you know is relevant. Usually reducing the feature space does hurt performance, but it should improve generalization if you know that you're restricting the feature set to things that are related to the thing you're interested in qualitatively, so it can help to prevent overfitting. And then other document applications apart from classification would be unsupervised clustering of documents. So you can represent each document as a vector using something like doc2vec, which is like word2vec, but for short documents, and then cluster those using TSNE or something like that. And then topic modeling, you're probably familiar with, which extracts sets of words from a collection of document in an unsupervised way. So it finds clusters of words in documents where each cluster of words should relate to a particular topic. And then over time, you can measure the amount of each topic in each new document. So this is an example of a topic model visualizer. This is a Python package called PyLDAViz. And you can see there in the middle, those phrases, balance sheet, private health insurers, relate to one particular topic that's highlighted in the visualization on the left. And that tells you which phrases make up that topic. And then for a set of new documents, you can say how much of the new documents, what proportion of the new documents are made up of that topic. And that means that you can measure changes in topics over time in future documents if you split the document set up into subsets according to, every 6 weeks or something like that. A lot of the difficulty with this kind of model is that the examples are typically to do with a bag of words. So you just split each document into individual words. But for most applications, single words are not particularly useful. So if you look at this example, which is to do with prudential news announcements from prudential regulators in the EU, you can see things like balance sheet life insurance, friendly societies. The word friendly or the word balance or the word life out of context there don't really have the meaning that you're looking for. So a lot of the work is in identifying these multi-word expressions first, which is what the kind of entity recognizers and the keyword recognizers in GenSim and Spacy can do. Okay, so this is an example of a little bit of Corlytics class taxonomy. So this is the regulatory category taxonomy, and you can see it's hierarchical. One top level category is corporate governance, another one is financial crime, and then there are subtypes of those. So the regulatory category relates to what type of crime, what type of regulation was broken. So there are some regulations against bribery, there are others to do with corporate governance. There are different types of regulation. The service line hierarchy is a different it relates to which area within the financial institution is responsible for the breach. So you could have a money laundering breach in the insurance line of the bank or a money laundering breach in the equities line of the bank. So they're different areas of the business rather than different types of regulation break. And the hierarchical multi-label nature of the data set makes evaluation very difficult. It's not as simple as, you have three classes and each document has one class. That's a typical textbook example. Measuring how well an algorithm has done on a label set like this is tricky, and that's what I'm going to talk about for most of the rest of the talk. And I also think that the evaluation task is a bit underrated, both in academia and industry, but especially in industry, because the process of evaluating which algorithm does best is different from the process of evaluating how well the algorithm solves your business case, and there's a lot of trade-offs involved. Another thing to keep in mind here is that these are often non-natural categories. What I mean by that is that this is a taxonomy of regulatory categories that has been devised by human experts. It's not really a natural distinction in the world. So for a textbook text analysis example, you might think, is a newspaper article about sport or is it about science? And one kind of natural distinction there is which section of the newspaper did the article occur in? Did it occur in the sports sector or the science sector? And that's that's a definite checkable thing with an exact answer. But out of that context, is an article a sports article or a science article? Well, it might be very clear for 3/4 of documents, but then there would be some documents that are about drugs in sport or timing in sport or something, and it's really not clear, and inter-annotator agreement might be low. So that means if you give two experts the same document, how often will they agree on all of the categories? So that really depends a lot on the data set, the domain, and lots of things like that. And a lot of the problem here is to do with imbalanced classes. So you have a few examples of some categories and some categories that you have a lot of examples for, and that's what complicates evaluation particularly. So I'll talk through some of these metrics now with this next example, trading off precision, recall, F1, and accuracy, and false positive rate. And usually what I found is that deciding what is the best metric and deciding which is important for the business case, those decisions are probably more important than exactly which parameterization of your algorithm to use. Okay, so here's a hypothetical example of two classes, and for each class, so there's 15 documents in total here, and this is a multi-label data set. So in the last document there, you can see the document is true for the true class is positive for both classes. And this is what makes the evaluation tricky. We have true negatives, that's cases where the label should not be present and the algorithm correctly didn't apply the label. We have false negatives where the label should have been applied, but the algorithm didn't apply it. True positives where the label should be there and the algorithm does predict it. And we also have false negatives where the algorithm, the true label is there, but the algorithm didn't predict it. And precision, recall, and accuracy measure different combinations of these. So precision is sometimes also called specificity. So of the things that the algorithm predicts should be true examples of the label, how many of them actually are? And recall is sometimes called sensitivity. So of all of the ones it should have labeled, how many did it? And whether you care more about precision or recall just depends on the business case. So you can think of like maybe a fraud alert system where if you falsely predict that a document is an example of fraud, it's not a big deal. You can just get a human to check it. But if you fail to predict it, then you miss a big fraud, and that's a big deal. In that case, a false positive isn't as bad as a false negative. But there are other cases where false positives can, just make the system look really bad. If you're claiming that you've got an automated system trained on high quality data that can be used to make decisions, but then it's got wrong labels predicted for lots of documents, that looks bad too. So you can use a lot of these metrics to compare which of your algorithms and which of your training set combinations performs better relative to each other. But I think for the business application case, it's also important to do a qualitative application or qualitative evaluation. So that means implementing the system and testing it through a user interface the way a client or a user would use it. I'm just saying, impressionistically, how often do you see errors? And especially when you do see an error, is it a label that experts might argue about, or is it a label that experts, that a label that has clearly got wrong? Those kind of distinctions are important. And in the classification I'll be doing for Corlytics, I focused on the high-level categories because obviously you have more examples for each high-level category than the lower-level ones. And that will be okay for some applications, but not for others. I've talked about inter-annotator agreement. I've said that already. Yeah, and then the classification threshold can be adjusted with reference to the precision recall curve. So what that means is that each of these systems, whether it's a neural network or a scikit-learn system, will actually give out a continuous prediction. So for each label, it will give you a number between 0 and 1 that says how likely it is that the document should have this label. And then in practice, what you do is you say, if the continuous prediction is greater than a threshold, say 0.5, we apply the label. If you increase that threshold to 0.8, what that means is that it needs to be more certain, in effect, to give the label. So that means if you increase the threshold, you would get fewer false positives, but of course you'd get more false negatives, more misses. And most of the scikit-learn algorithms by default optimize for accuracy. So there's options in there if you prefer to optimize the threshold for precision, or you can adjust the threshold with a custom function. And that metric, with reference to the curve, sometimes you use a precision recall curve, sometimes also called a receiver operator characteristic curve, where you can plot the false positives against the false negatives and find a good point. Okay, so for the software of these algorithms that I've been talking about, I've mentioned Hugging Face and scikit-learn. For the scikit-learn systems, there's lots of great examples out there of how to do cross-validation, both to separate the training and the test set, and to optimize parameters like for a random forest, how many trees to use, or for a support vector machine, what the regularization should be. So there's lots of examples online, lots of code online for those. And for document classification, those approaches work almost as well as the deep neural network approaches, because the deep neural network approaches, where they've really made a lot of progress, is on short amounts of text. So translating sentences, recognizing speech and things like that. They're typically designed to take in input in chunks of about 512 words. So for these documents, which could be 4,000 or 5,000 words, there are some ways of chunking the documents and averaging over the chunks to get the correct prediction. But I've found that the scikit-learn methods work almost as well. I'll show some results now. So this is for the service line category, the top 8 top level categories in Corlytics taxonomy. And we can see there the metrics I've chosen to show are precision, recall, F1, false positive rate, and accuracy. F1 is a type of average of precision and recall, the balance of precision and recall. This is for using a random forest with a bag of n-grams, so using up to 3 grams, three word phrases. Yeah, so the important thing to keep in mind here is the accuracy is per category, and then you can either average that by taking the average of the accuracy across all 8 categories, or you can work out the overall average, treating it all as one data set. So that means that classes where there are more examples will have a bigger influence on the average. And what's important to keep in mind here also is, even if you have a high per class accuracy, so for the insurance category, 97% of the time it gives a correct prediction. Remember that for each document, you have to predict for each category. So this is a binary yes or no, 0 or 1 for each category. So if you have to predict 8 times because there's 8 categories, even a 5% error rate is quite high. So in this case, at the bottom there, where I have 40% document error, that means 40% of the documents in the test set using cross-validation have at least 1 error, and 8% have at least 1 false positive. Again, to get an idea of how damaging that is in a case where it would be put into a product, you need to get an impression of what the nature of those false positives are, if they're really obvious examples or if they're borderline cases. So I won't talk through all the results. I'll just say that I tried random forests, support vector machines, ridge regression, regularized regression, and the results are all fairly comparable. The random forest output gives you this nice visualization, or it's possible to get this visualization out of it, which will show you each feature and the TF-IDF threshold for the feature and which way that that sends you down one of the trees to get to the prediction. I also tried a convolutional neural network that's implemented in Spacy. It gives a similar accuracy for the service lines. This is the overall accuracy. The regulatory category taxonomy is more difficult in general. So this CNN categorizer gets 89% accuracy. That was about the score of the best random forest or SVM method too. The reason the regulatory category problem is more difficult is just to do with the type of category it is. If you think the service line is about the branch in the bank responsible, so as I said, whether it's insurance or pensions or equities, so it's kind of like a topic. If the word insurance is mentioned in it, you can be, there's a fairly straightforward relationship between the topical words and the category. With the regulatory category, whether something is an anti-money laundering violation or a corporate governance violation, these cases are kind of by their nature adversarial. They involve cases where people were trying to be just on the right side of the law. they may fall between categories, and it really takes an expert legal analyst in a lot of the cases to say not just which regulatory category is discussed, but which regulatory category breach caused the enforcement to be applied. So it consistently, no matter what system I've used, the results are much better for the service line taxonomy. And that's some of the other results. So you can see the document error is much higher for the regulatory category. This is an example of the feature interpretation from the support vector machine for the service line insurance using a different kind of feature. So the results I've shown so far that got the best results were using 1, 2, and 3 grams. So every combination of single words, 2-word phrases, and 3-word phrases that occurred more than 10 times in the whole corpus. So whether you use more than 10 times or more than 5 times, that either gives you around 40,000 features or around 100,000 features. I also tried doing a kind of more restrictive feature selection method using NLP that picked out keywords, entities, syntactic verb-noun combinations and things like that. That gives around 13,000 features, but the accuracy is lower than just using the dumber method with more features. So maybe it would generalize better, but at least on cross-validation, the performance is worse. This is an example of those features that are predictive for the insurance category. So you can see it certainly is fitting to features that at face value look like they're related to the category. There's a mistake at the top there. That's actually the linear kernel, not the RBF. You can't get feature weights from the RBF kernel. Okay, just briefly, I'm kind of gone over time, but another thing to mention here is semantic search or information retrieval. So I've discussed this problem as a classification problem where you take each document and say whether it belongs in a class or not. You can also view it as kind of a retrieval problem. Like I want to search for documents related to corporate governance in this database. So that's kind of you know, that falls into a different domain of NLP really, information retrieval. And there's kind of a standard method called BM25, which is a Python library for, and there are neural semantic search methods. So my advisor in UCD is David Lillis, and one of his PhD students, CC Wang, has a nice demo online of this neural semantic search applied to a data set of COVID science documents. So I'd recommend checking that out if you're interested in the information retrieval or semantic search approach. Okay, and just to finish up, I've said already, you know, evaluation and kind of quality assessment is I think even more difficult in industry than in academia, where you kind of have agreed on benchmarks and you don't have the added complication of extrapolating from, you know, even once you've decided on what the best performance quantitatively is, you have to then try and optimize that to the business goals, the business aims, what clients want. So it's really, I think, the most important aspect of the whole process. And data quality and the homogeneity in the data is more important than the choice of learning algorithms. So, you know, when you kind of visually read the documents in the different categories, you can see that how clearly the category is a homogeneous concept influences a lot how well the algorithm performs. Obviously, remember to use cross-validation and not to leak information that won't be there at test time. So, you know, this is easy to do, especially if you just use a cross-validation and don't use a validation, held-out validation set. You shouldn't tweak parameters that if you put the system into production, new documents, you won't be able to rely on predicting them. And you know, even now compared to when I was a PhD student, it's much easier to look up a really cutting edge algorithm online and find a well-documented, robust open source Python library out there to work with it and example code. So this stuff is very accessible, maybe except for the very latest neural methods. Okay, so thanks for that. And I'll take any questions that you have. I think you can unmute yourself if you'd like to ask a question.